Hello guys, KNOCKCAT this side. So today we are going to solve gfgpotd of the day, and that is count pairs sum in matrices. So I hope you have already read the problem and tried by yourself. If not, I will definitely suggest you to go through the problem at least once. So let's come to the problem. The problem says we are given two sorted matrices, mat1 and mat2, and both are of size n cross n. Two sorted matrices, one observation needed to be taken care. Each matrix contains number arranged in strictly ascending order. This is another observation, with each row sorted from left to right and the last element of row being smaller than the first element of the next row. What does that mean? That the matrices is sorted in ascending order. That means, and it says the last element of a row being smaller than the first element of the next row. What does this mean? That if I flatten this matrix and write 1, 5, 6, 8, 10, 11, and so on, this will be a complete list which is in ascending order. It's saying that with each row sorted from left to right, we can see left to right they are sorted, and then the first element of the next row, this 8, is less than the last element of the previous row, being smaller than the first element of the next row. Last element of a row being smaller than the first element of the next row. It's clearly mean if I flatten down this matrix into a 1D array, this would be a whole sorted list in increasing order. Now, we are given a target value x. We have a target value x, and our task is to find and count all pairs AB such that A is from mat A and B is from mat 2. Now, what we want to do, we want to actually find all the pairs AB such that A would be from matrix 1 and B would be from matrix 2. And what we have to do, such that these A and B equals to X. That means I need to tell the number of pairs ij such that mat 1 of I mat 1 of ij, that's a two element, because matrix would be like ij, and mat 2 of some index. These sum should be equals to my x, and I need to find those pairs, how many pairs are possible. Clearly have to take one element from this, another element from this, and count the number of pairs, or let's say the elements, or not elements, that sum to an x. So I hope the problem is clear. Let's come to the test cases, and it will help you visualize more. So okay, I have taken this case here. Here we can find this is a whole list 1, 5, 6, and 8, 10, 11. This is whole and sorted in increasing order. Two observations that I want to make here again: sorted and strictly ascending order. Strictly ascending order means there is no value duplicated. There is no value duplicated. It is strictly A should be strictly less than B. There cannot be a case that A is less than equals to B. So there is no two values same in any of the matrices. One more observation. So now let's see how many pairs we have. So if I take 1 from here and I take 20 from here, I can actually form 21. So we have 1 comma 20, and 1 is from mat 1 and 20 is from mat 2. Okay. Another, if I take 5 from here and 16 from here, again I can form 16 and 5 sums to 21. Again, if I come to 13 and 6, they have a sum 19. This is not a common pair. But if I take 11 and 10, this is actually 21. 11 and 10. So I got third pair. And if I take, let me find another pair. 12 and 8 would be 20. We cannot find. 13 and 8 would be 21. Okay, yes. 13 and 8 would be 21. So we find 4 pairs. So I feel 4 is the answer, and we find 4 pairs. So these are the 4 pairs. One element should be from this matrix, one from this, and their both sum should be equals to x. So 4 pairs of AB are possible. If I consider this case, we need to find 10. So if I take 1 from here, 7 from here, it is 8 only. If I take 7 from here and I take 3 from here, then 3 and 7 definitely form are 10. And again, if I take 6 from here and 4 from here, So these actually make 10. So I think the question is now clear. So if we think of a very naive solution, the naive solution would be iterating our matrix mat1, let's say from I to n, and again nesting from j to n. By this, I can access each element of mat1, each element of mat1. Let me write it clearly. By writing this syntax, I can clearly access mat1 element of ij, and now I have to find this mat of ij would make pair with which element. So, and the next element I need to find in my mat2. So I know A would be nothing but this. A would be nothing but mat of I j. This is mat 1, okay? This is mat 1. And now I again can do a brute from 0 to n, and again from 0 to n. This will actually access me. This will actually access me all the elements of my mat 2. And now here B would be, let's say this is K and this is L. Now B would be mat 2 of K comma L. K comma L. So now I got A is this, B is this. After extracting this A, I do a nested for mat2 so that I can access mat2 elements, and now I can clearly check, do my A plus B equals to my X. If that's the case, plus plus count. I think this would be a very trivial approach, and all you have thought of this solution. I will definitely show you the code for this. So what I did, it's passed 110 case, sorry, 1010 cases. So the same thing, I and j, iterating this have access me mat of ij, because I and j, this would be given me A, this part. And for K and L will give me an element from B. So now I'm checking if my A is A plus B equals to X. If that's the case, I can do a count. Now why I have taken these flag variables? Because there is no duplicate elements. There is no duplicate elements. A cannot be, they cannot be duplicate elements. There will always be X and a Y pair. There would be an X and Y pair. There would be always an X and Y pair, and since there is no duplicate, so if I find X here and Y here, and they both sum to some value of target, then I know, since there is no Y again, so this X will never form pair with any, because the next element would always be greater than Y. Let's say Y plus 1. The next element after Y is always greater than that. So if I already find a pair XY which gives me a target, then since there is no Y that is coming in the list, I can easily break, because the next element would be greater than this, and if it is greater, then X plus Y plus 1 would be greater than my target. So I have said, okay, starting of this, make false, because I know I have A here. Anytime if I find a pair, make my flag true, and then if flag is true, do break, so that we don't need to iterate again. And at last, as we are doing count here, return count. This is a very trivial, nice solution for this problem. Let's come now to the observations. So, can you think of something so that we can optimize this problem? We are looking for a pair such that A plus B is equals to X. We are looking for something A plus B equals to X. So now my question to you is, have you solved this type of problem earlier? And the answer would be yes, most of you have already solved this type of problem. This is nothing but two sum. This is nothing but two sum. You have one value A, you have one value B, and you need to find A plus B such that it gets you X. Now, why problem solving becomes important? Because it's more about how you can mesmerize, or how you can think of ideas that you have already solved. If you can relate this problem with two sum, this you have already solved this problem in a very intuitive way. What does mean? Two sum is actually we find A plus B equals to X. Let's say if I have A with me, we already know X. We already know X. Okay. So if I say B would be X minus A, just basic math, B is equals to X minus A. So if I can iterate on A, I can iterate on A and can check Do my do my x minus a present in an array? Do my x minus a is present in somewhere? So what if I have added all these elements into my map or a hash map or a set? If I've added all these elements into a map or a set, so I can only iterate these number of elements. I can only iterate these number of elements, and let's say all A's all A's are already in my set or a map. All A's are already in my set or a map. So whenever I would be iterating from here, I already know X, and since these are my all B's, I can say, okay, do my set contains, do my set, do my set contains X minus B. Do my set contains X minus B. Is there a valid pair such that I have X minus B because X plus, because A plus B is equals to X. So if I was iterating on B, so can I get A is equals to X minus B? So I will say, okay, I have X minus B. So I now the value for A would be X minus B. So do my set contain a value A? And if my set contains a value A, if my set contains a value A, then I have find a valid pair. Then I have find a valid pair. So let me do a dry run for you of this as well. Let me consider this case only. The video might be too long. It can be because my idea is not to my idea make is to make you the understand the concept very clearly. Here I'm enforcing towards do you able to relate to the problem that you have already solved, that is two sum, and this is actually two sum. Okay, we will do like a bit fast. Okay, let's say I have one, so I am saying all these elements are already in my map or a set. Any data structure you can take. Set or map would be preference. You cannot take anyone. That will help you to retrieve value. Okay, now I would get 8 and I know 21, so I would check 21 minus 2 exists or not. 21 minus 2 is 19. We don't have 19. I move to 4. I will check 21 minus 4 exists or not. 21 minus 4 is I think 17. 17 do not exist. We move to forward again. Similarly, I came to 10. 21 minus 10 equals to 11. Does it exist? Yes, 11 is exist. So I find a valid pair. Let me move to another. 16. 21 minus 16. Do is exist? 21 minus 16, I think it would be 5. Do 5 exist? Yes, 5 exists. So that means my 16 and 5 will form a pair. And if I come to 20, I will say, okay, 21 minus 20. Do my 1 exist in my set? Yes, 1 exists. So I have find another pair of 1 comma 20. So this is nothing, just two sum, giving you a complexity. Okay, so the last, when I do 4 loops, it was actually n raised to the power 4. Okay, n raised to the power 4, the brute force one. For this, actually you can, n in n square, you can actually do, in n square, you can actually put these all elements in my set in n square log n, in n square log n, n square log of n. Okay, and then for checking this again, it will again take you n square log of n. So overall, the time complexity for this problem would be n square log n. Why n square log n? I use a map. Some of you may tell that I use a unordered map that will give me an order of one, but that's not true in all case. That it gives order of one. Unordered map also have a time complexity of order of n in worst case. I don't prefer using unordered map, though it's good for use to tell the interviewer that I can actually optimize using this. I prefer using map only. So by putting in my all elements in map, it would definitely take me n square log n because I would be having n square elements. And for checking all these, I would be checking again n square for iterating and log n again for checking does my b minus a, does my x minus b exist in my map. So n square log n. Space complexity will be order of n square because I am putting these elements in my map or a set. So let's come to the code. I don't want to waste much time in these. It's just like you know how to solve two sum. I've taken a set. You can take any hash map, or you can in Java you can take hash map, dictionary, anything. I have taken a set and I insert all the elements of mat1 in my matrix. And now what I'm doing the same thing that I taught you, just have a dot count is a function in STL that actually checks do this element is in my set or not. It returns true or false. If it found, it's turned true. So x minus mat to 5j. I know x is nothing but my target. And now I'm saying x minus mat to 5j. If this is present plus plus count, the same thing that I want to show here. I've erased, but I think you are getting it. So if this is nothing, but if x minus b is which is equals to be a, does I have a such that its value is equals to x minus b. So if I have a value a in my set, then this b and a will form a pair. So plus plus count. So this is just two sum. Now let's come to a better approach. But if you can do two sum, you are actually on a right path because you are thinking intuitively. You are using your past knowledge to solve problems. Third, one more observation again. There are sorted elements in each row. Sorted elements in each row. That means sorted elements, sorted elements in each row. Can you, can I do something like we have sorted elements in each row? Can, okay, let's say I'm at one. Can I have a pointer here? We have a sorted list. We have a sorted list. Can I have a pointer? Can I have a two pointer type approach? Can I have a sorted list. I need to actually find does a plus b is equals to x. Does if a plus b is less than x, do plus plus I. Or if a plus b is greater than x, do minus minus j. Have you remember this? Do you remember this idea? This is nothing. This is also one way of doing two sum only. Using two pointers, you find valid pairs such that x plus y is equals to x. Oh, sorry, target. Okay, take it target. You have a sorted list. You have a sorted list. One pointer is here, one is here. Do their sum equals to target? If yes, plus plus count. If it is greater, because since this is a greater side, decrement my j pointer. If it is the sum is coming smaller than target, that means I need to increase my sum. And since I is sorted from increasing to decreasing, increase my pointer to here. Two pointers. Yes. If you have solved two sum, you also know this idea. But if not, let me recall. I have tell you what actually we do. Can I have a pointer here? Let's say ij 0 0. I have a pointer here, supposing 0 0. And let's say I have a pointer here also. This is at n minus 1, n minus 1. Name it as ij. Name it as xy. Can I do the same thing? Can I do the same thing that if my element at ij and element at xy is equals to x is equals to x, that means I have find a valid pair and do a minus minus count. And since I have find a valid pair, decrement my y, decrement my y. Now my y would be here, x remains same, and my remains same because I is the row and j is the column. J is increment. Okay. So and if again if sum is getting smaller, if sum is getting smaller, that means I need to increase. I need to increase. I will again move my pointer to here. Again, in this case, this will not happen. Let's do the dry run only. Let's do the dry run only. I'm at here. Let's have a pointer n minus 1, n minus 1. I'm at here, and let's say a pointer is 0, 0. 20 and 1, 20 plus 1 is actually 21. We find one pair. Now it's point to here. Now my coordinates are here, and again for here, my coordinates are here. My coordinates are here. 5 and 16 is again 21. 5 plus 16 again 21. That means I find a valid pair. Move my pointer here. Move my pointer here. Move my pointer here. 6 and 13. 13 plus 6 is 19. 13 plus 6 is 19. 19 is actually less than 21. That means I need to find, increase my sum. I need to increase my sum. I will move to, I have to come here. I have to come here. I have to come here. But now, let's say if you have a pointer 0, 0, at this point, you are at 0, 3. And now the next element you have to come is 1, 1. Sorry, 1, 0. You are at 0, 3. And now you have to come at 1, 0 because next element is 8. You don't have any elements further from here. So can you write a small condition? Can you write a small condition that okay, if my j equals to n, if my j becomes equals to n, that means it is now coming to the boundary. It is asking my next element, increment my y and make my j to 0. Do this, uh, just this small condition do the job for you to bring your pointers here. Yes. actually it will do 0, 3, 0, 1, 2, 3 is at the 3 is equals to n. That means now increase my row. Row was actually 1. Now row become 1. J becomes 0, 1, 0. Actually, this is 1, 0 only. This is 1, 0 only. Just small case, just small case, just a small case. I am at 8. Okay, now check. 8 plus 13. Yes, it is 21. It is 21. Decrement my pointer. Decrement my pointer. Now the pointer should have come here. Should have come here. And this pointer should have come here. This pointer should have come here. But this pointer should have come here. But how will you bring your pointer here? How you will bring your pointer here? Can you write a small condition again? That if your this was xy, y was the column. If my y is becoming less than 0, if my y is becoming less than 0, I have to come to the above row. I have to come to the above row. Do my minus minus x and make y equals to n minus 1. Okay, this case, it was actually 0, 1, 2. It was 2, 0, 2, 0. And when we come here, it becomes 2 minus 1. 2 minus 1. Y is less than 0. Y is less than 0. Make my y to n minus 1. Make my y to n minus 1 to this row. And decrement my row. Decrement my row. Now I am at this row. I am at row 1 and my y is n minus 1. Just by a small condition. If my y is less than 0, decrement my row and assign my y to n minus 1. Because I need to come here. A small case. A small case. Just small condition. And we just thought of along the way. Now I'm at here. 10 plus 12. 10 plus 12 is 22. It's 22. It is actually greater than. It is greater than. That means I need to decrement my pointer here. It will come to here. 10 plus 10. 10 plus 10 is 20. It is less. It is less. That means I need to increment my ith pointer here from left hand side. This is left hand side. This one is left and this one is from right hand side. Okay. So let me erase all these stuff. All these stuff. I'm at 10. I'm at 10 from here. All these stuff. I know that I am at 10. Now 10 plus 11. 11 plus 10 is 21. Yes, is 21. That means I need to come to the next element and I need to decrement to 9. Now I am at 9. Okay, again my j is equals to n. What I have to do? What was the condition? Plus I and make j again to 0. Plus I. Okay, I will come here and j will again be 0. I came here. I came here. Small conditions. Small conditions. Here I am at 19. 9. 15 plus 9. 15 plus 9 what? 9 plus 5 14. Yes. 24. I am actually getting greater. And when I got greater, decrement here. Okay, again my y is getting 0. So I will do that condition that if my y is less than 0, decrement my x previous row and make my y is equals to n minus 1. Okay, just and now I'm at 7. 15 plus 7 again 22. Again we are getting greater answer. Come here. 15 plus 4 19. I am getting less. I am getting less. Increment my I pointer. 16 plus 4 20. 16 plus 4 20. I am getting 16 plus 4 20. I am here. 16 plus 4 20. I am getting greater answer. Sorry, small, less than 21. Increment my I pointer. 18 plus 4. 18 plus 4 is 22. I am getting greater answer. Come to 2. 18 plus 2 is 20. I am getting less answer. It's come to here. And now when my x is also pointing at n and y become greater than n, I can just break. When my if my I becomes greater than n. So in this case, when it's go, now my I will point here, somewhere here. But we don't have element. So if I is greater than equals to n, or if j, yeah, if I is greater than, this case would be fine. And from here, if it was, let's say, x and y, if my y becomes this my x row. If my x was less than 0 and my y also become less than 0. Although if my x becomes 0, next time y will be pointing here, but since we don't have x, a small condition. I hope the try and it was 2 pointers only. Let's come to the code directly. This time I will retrieve my, because it was the last accepted code. This is, don't be afraid. It is just small conditions. What I did, Have a pointer I equals to 0, j equals to 0. Have a pointer I equals to 0, j equals to 0. And the pointer at last element. The pointer is at here and the pointer is at here. What I did, make sum. Okay, do I plus j plus j. Same condition till my I is less than n. I should be less than n because if I come to a point where my I become 4, I have to break. And same, if my j also becomes to n, because this time we don't, till my I is less than n, we don't need this case also. And my x is greater than 0. We don't need this case. This would be fine only. If my I reaches here after 15 rows, I don't have elements in my mat 1. Or if my j pointer, if my x pointer actually come to a row -1, that means my elements at mat 2 is finished. So in sum, what I do, pointers at here, pointers at here, pointers at here, do plus, yes. If my sum equals to target, if my sum is equals to target, okay, plus plus count, we find an element. What we need to do, plus plus j, yes, because now I have to come here, plus plus j. This was ij, plus plus j. What I'm checking, the same case, if my j, this is the case, if my j would have come here, if my j would have come here, do plus plus I, come to here and make my j equals to 0. Do plus I, make j equals to 0. Since I also have to go beyond here, I have to come behind also. So minus minus y, because is for the column. If my y is become less than 0 at some point of time, do my y again point at n minus 1 and decrement my row. Make my row here. Just two cases. Increment the count plus plus j minus minus y. Come here, come here, come here. If we do the same, if we find a pair, decrement from increment from I, decrement from j. But handling these two cases. If j equals to n, come to next row, and if y is less than 0, come to previous row. Those things only. I explain these. If my sum is less than target, that means I need to increment my I, because this will increase the sum. So again, if I increase the j, because ij is here, I have to move here. So if at some point j come out, I have to come to next row. Same condition, same this condition also here. If some point j becomes n, come to next row. And now this case, this time if my greater, sum is greater than target, that means I need to do minus. So I will come to previous element. But what if previous element comes after 13 here, and we don't have element here? So I need to decrement my row, that is minus x, and make y to n minus 1. Just those cases. I have to decrement my, I will do minus minus y, because if that's not the case, because if I am at here, I have to come here. If I am at here, I have to come here. But if I am here 13 and I come here, so at this point y is less than 0. So if y becomes less than 0, make my y to n minus 1 and decrement the row. Decrement the row to the previous row. Previous row last element. So that's it. That's it. Return count. Return count. I think this should be working. I also I removed these two cases. Let me check 4, because I think we don't need them. I think we don't need them. Let's check. Yes, we don't need them. We don't need them. So I think the code is clear. The code part is clear. Actually, earlier I was using these two also, but now I realize that actually we don't need these. For J and Y, we don't need. So this is the code. 2 pointers. If you know 2 pointers, this question is a really good question. It is actually two sum only, but in two sum this is not a single array. It said I have two arrays. Take it like that. It is two sum only. So I think this problem makes you some learning, and you get to learn two ideas. One is of two sum, that is using map, and another is of 2 pointers, that is on the condition that the matrix is sorted. If the matrix was not sorted, then you would have not used this logic. If the matrix was not sorted in increasing order, then you cannot able to use this logic, because this based on the condition, if sum is less than, that means I need to move my I. And if sum is greater than, if that means I need to decrement my j. Then if it is not sorted in increasing order, then the only approach we have is the map approach. And that is putting all the pairs in a map or a set, and then check if I have x minus that pair in my map or not. If we have, plus plus count. So this is all about the problem. This is all about the problem, and I hope you get, get to learn. So that's all from my side. I will give the code in the description, and if you have any doubts, you can comment on it. And that's it. Not yet this side.